Hi students, welcome to Preliminary Chemistry and Metals video number 20, and this one is looking at calculating gas volumes. Now unfortunately this one is one that you will need to know. So what we're going to do is we're going to look at how we use our knowledge of stoichiometry and the use of mathematical calculations in chemical equations to help us to calculate the volume of a gas produced in a chemical reaction. So one of the simplest ones that we can look at is the hydrogen gas which is produced in a reaction involving an acid and a metal. So magnesium is a type of metal and hydrochloric acid obviously is an acid, and we know when these two react together they will form a salt plus hydrogen gas. So what we're going to do is see if we can identify how much hydrogen gas should be produced, at least theoretically, from 12.15 grams of magnesium. How do we do that? Well, the first step is always going to be to write a balanced equation for this reaction. So we need to make sure that the equation has all the components in it. And we're going to have to start looking at these subscripts as well now. They're going to become more and more important as time goes on, and if you can get into the habit of using them early, it's going to be a good habit for much later. So we need to write a balanced equation. So in this case, magnesium solid reacts with hydrochloric acid, which is aqueous, that is, it's in solution, and it forms magnesium chloride, which remains in the solution. It's not a precipitate, it doesn't come out, and hydrogen gas, and we see the hydrogen gas as bubbles. So this is the bubbling that we see, which we can test with our pop test. So once we've balanced the equation, we need to make sure that the equation is properly balanced, and we need to make sure that we look at things like salts, that they're written in the correct format. So that is, from the periodic table, magnesium has a +2 valency and chlorine has a -1 valency, and therefore the formula is going to be MgCl2 to keep the charges balanced within this particular compound. Hydrogen gas is always written as H2, but metals, on the other hand, are just written as their symbol, as they are metallic arrays. So the simplest or empirical version of that is just a single magnesium. When we balance the equation, we get something very important, the mole ratio, and it's worth writing the mole ratio underneath your equation because it is going to be critically important to your success in stoichiometric calculations. So to write the mole ratios, we need the coefficients in front of each chemical. So the coefficient in front of the magnesium is 1. The coefficient in front of the hydrochloric acid is 2. The fact that there isn't one in front of the MgCl2 means it's 1, and likewise for hydrogen. So the mole ratio for this particular reaction is 1 to 2 to 1 to 1. Now, when we want to actually calculate the mass or the volume, then we need to be aware of the fact that we're going to have to start with the mass of the magnesium, because what we need is the number of moles. The number of moles is the most critical concept that we have in chemistry, and it allows us to do conversions between moles and masses and moles and volumes, and later on we'll also see that we can use it for the calculation of concentrations as well. So in this case, the mass is what we are given in the question. So this is what we had from the question, 12.15 grams. The molar mass comes directly from the periodic table, which you're always given. So you don't need to memorize them, you just need to be able to look them up. And when we look up magnesium, we find its molar mass is 24.31. Now this is going to round out to pretty close to 0.5 moles of magnesium. Now this is where our mole ratio is critically important. If I just remind you of these 1 to 2 to 1 to 1, then what you can see is if we have 0.5 moles of magnesium, then we must have 1 mole of hydrochloric acid reacting. We must have 0.5 moles of magnesium chloride produced, and we must have 0.5 moles of hydrogen gas produced. So in this case, if X represents the number of moles of hydrogen gas, then because the ratio is 1 to 1, it must be 0.5 to 0.5. So X in this case must be equal to 0.5 just because of that mole ratio of 1 to 1. Now the final step is for us to actually look again at our data sheets, our periodic table, but on the opposite side. Because if the reaction was carried out in a laboratory under standard laboratory conditions, that is 25 degrees Celsius or 298 Kelvin, and 1 atmosphere or 100 kilopascals of pressure, then 1 mole of hydrogen gas, in fact 1 mole of any gas, will occupy 24.79 litres. The moles ratios is going to be consistent. That goes back to Gay-Lussac's law. So 1 mole of any gas is going to occupy 24.79 litres. What that means is if we have half a mole of hydrogen gas, it's only going to occupy half of that volume, which is 12, rounding up 12.40 litres. So that is to say we would have 12.40 litres of hydrogen gas produced. Now obviously we'll do a number of these questions in class to help you practice with this with a little bit more, but this is fundamentally the theory behind the calculation of gas volumes in chemical reactions. Thanks for watching.